Okay, everyone. What I promised to do today was a quick little video of the last part of Unit 6. I'm going to do pretty much a summary. We're not going to spend too much time worried about the ins and outs of these things. It is a review of what we did before spring break, so that'll be helpful for you. And the homework that accompanies it won't even require you to use a calculator or anything like that, just to think about your problems. So, this last part of Unit 6, it's called paired samples and blocks. Basically, the reason it's nothing different is you can see right here in this paragraph, it says sometimes data is not independent. So, in the event that you have data that, for instance, is about people who are in a married couple or are related, and they might share similar interests or have similar DNA if they're related, or if you're looking at time, meaning like pre-test, post-test, or if you're on track, let's say your time before and then time after implementing a training regimen, those are all related to each other. So they're not exactly independent. And when that's the case, we call it like paired data. Now, it's not a new test, it's not a new concept. You just, by saying they're not independent, they are paired, and then you do the following. So you basically treat those matched pairs as a single set of data, and you subtract your before data from your after data to see if there's like an effect on it. So what is set up here, this is just for your information. If you're doing an experiment, this is going way back to Unit 3, end of first semester, you might remember blocking, where remember we said if gender might play a role in the effects a drug has on treating a disease, you might block to account for that. So that data is separated into like two categories, but you're still studying the overall one effect of it. And if it's an observational study, they might use the words matched pairs. This is really just more of a vocab alert. You don't really have to worry about that. The main thing we're going to be looking at is what do I do if my data is not independent? How do I treat it as a single set of data, which they kind of say up here? And then why it's nothing new is once you subtracted data, and we kind of practiced this a little when we examined um, like proportions with two samples, but regardless, you use the one sample t interval or one sample t test. So, long story short, if your data seems to be related, thus not independent, you would subtract the two sets of data into one set and then do a one sample either interval or test depending on what you're looking for. So here's an example that I have here. It says you're trying to determine if Olympic speed skaters are at an advantage if they skate on the inner or outer track. So I don't know a ton about speed skating, but there is an inner track or an outer track if you were trying to like get around someone when you're passing them. And so these two times here are if they strictly did the inner lane and strictly did the outer lane, was there a difference in their times? So because this is the same racer, it's just two different um, elements of the same racer, you would treat this as a single set of data. So you can see here sometimes someone's inner speed minus their outer speed is positive, sometimes it's negative. And so we're trying to see if there's a significant difference between these times. So again, if you were presented this data, you could simply subtract the two and enter this in your calculator as one, which is what we're going to do, and you'll see that in just a second. But just like we've seen with any problem, there's assumptions and conditions that we want to check. So we're going to highlight those briefly and then move on and actually do this example. So you'll see here they call it the paired data condition. Basically, you'd want to say this data is paired. So that's pretty easy to write out and explain. And again, you can't just assume they are. You have to like think about the situation. And in this case, it's pretty obvious. Back to these independents. Notice it says if the data are paired, you want to make sure the groups are not. Oh, sorry, it says if data are paired, the groups are not independent, but you want to make sure that the differences are independent. So what they're saying here is there's no reason to believe the difference in speeds of one pair of races is different than for another. So even though the data from left to right are not independent, these from one to the other racer are independent, meaning none of these racers are like relatives, or something like that. That's pretty easy to kind of assume. Random, yeah, that's almost always a given. Now you'll notice here for 10% condition, it actually says it technically doesn't apply if it's an experiment where no sampling took place. Like this, that's kind of iffy. If you wrote independent slash less than 10%, I think you're going to be fine. What they're basically saying here is this is almost like an experiment where the treatment of inner and outer lane was like a given. So you'll see in the creating of this problem, the book doesn't even mention 10% condition. As far as I'm concerned, you can't go wrong if you just write that. So I wouldn't worry too much about that. And it's been a while, but if you remember, we talked about how you want to make sure when it's for means that your data are nearly normal. So how you do that is you'd basically make a quick little histogram of this data, make sure it looks normal enough. And if you remember from several weeks ago, we have basically 17 pieces of data here. This first one doesn't have a difference. The more data you have, the less it has to be perfectly normal because eventually central limit theorem kicks in. So here we go. There's a lot of talking. Let's see it in action. So there's our speed skater. Woo woo! There they go. Was there a significant difference in speeds between inner and outer track? So, first of all, this is all I'm really going to look at, and then I'll show you on the calculator how you would do this. So it says it's paired. Yes, it's the same racer, but different tracks. Independent. Yeah, each race was independent of the others. Cool. Random. Cool. And you'll notice they don't mention 10%, but again, I don't see why writing that would really be too big of an issue. Now, nearly normal. Yeah, this is a histogram of those differences. It looks pretty decent. Now, again, how would you find that? How would you actually check that and then do the work that goes with this? That's where your calculator would come in. So I've actually already went in and went to stat edit and typed in the differences in their times. Remember, if you want to see a quick histogram of that, you would go to second y equals, turn on that plot, and you would pick a histogram. And again, you might have to adjust your window. Now these are differences, remember? So we did have some negative ones. We did have some positive ones. I'm just going to leave it and see what it looks like. So you could zoom in as needed and adjust it a little bit. The one in the book, they obviously have a different window than I do, but this looks pretty decent. Nothing looks too crazy or skewed. Yeah, there's a gap here and here, but then you have a bar to the left and right of those gaps. So nothing looks unusual to me. I would just kind of proceed as normal. So I would have wrote my assumptions and conditions. You'll notice that, again, your null hypothesis is always that there is no difference, meaning the difference is zero. The alternative here, we didn't say the inner or outer was better. We just asked if they were different. So that's why your alternative is that it's not equal to zero. And again, that was the hard part. The easy part is doing the test. So we would go to stat, we would go to test. And because we've now subtracted and turned them into a single set of data, I would just do t-test. It's not going to say paired t-test on here. It's just t-test. So pick it. Your input was actual data from list one. Cool. The null, yeah, we said zero. The null is that there is no difference. And the alternative is that it's not equal to that. So we simply go down to calculate and see what we get. And you can see here, all right, your test statistic, t was 0.87, p-value 0.39, that's pretty big. And because it's just not equal to zero, this is a two-tailed test. And in a two-tailed test, you're looking for either a test statistic or p-value that would be underneath 1.96, or I'm sorry, a t-value greater than 1.96. We're clearly not there. You're usually looking for 0.05 here. This is way bigger than that. So yeah, there's not a significant difference. You would say there's not conclusive evidence to suggest that the inner outer track makes a difference on those speed skaters' times. If you want to see that by hand written out, that's what you see here in the book, but you could just use the calculator. So they come to the same conclusion we did. We would fail to reject that null hypothesis. Okay, now if you remember from prior to spring break, we did examples where I would give you the either physical data you type into a list or the summary statistics. So this is a summary statistics example where you don't have to do all that typing in to a list. So it says here, a study of British heterosexual married couples is trying to just find the mean difference in ages of husbands and wives. So they say a random sample of 200, but they only got 170 to respond, so 170 would be N, your sample size. And they tell you the mean difference was 2.2, standard deviation of 4.1. So we're trying to see if there's a significant, not a significant difference. You're trying to figure out what is the difference. So this one, because of the way they're asking the question, they want to know what is the mean difference. They're not asking if there's like a significant effect or something. You're probably going to look for a confidence interval. And that's what they say here. Again, this is a bunch of mumbo jumbo that you probably don't want to have to do. You're going to use a calculator. The only reason I put this in here is so you remember degrees of freedom is n-1. You'll type that into your calculator. So again, you would still check assumptions and conditions, all that stuff. You would discuss what you're studying, but then you would just use the calculator. So everyone, let's see what that would look like. Now again, we're going to go type this into the calculator. I just wanted to show you what the assumptions and conditions look like here. So again, your parameter is you're making a confidence interval to determine the true mean difference in ages between husbands and wives, in this case, Great Britain. Now, here, again, is the data paired? Yeah, they're couples. Is it independent? Now again, between the wife and husband, no, but between each couple, yes. Random, it says so. Now notice they wrote 10% here. This wasn't an experiment. You didn't like make people get married and then do something. This was just a study. So that's where you would mention this 10% thing. Again, if you're a little nervous about how do I know if I'm going to say 10% condition or not, as far as I'm concerned, you can't go wrong with just adding it. And then lastly, nearly normal. Now, if you're given summary data, you don't actually have an ability to make a histogram. So the book did. They did have all 170 couples data, which you can see is normal. But remember what we could simply say from inference. If you have 170, like means in this case, central limit theorem would kick in. And you could just assume that it's nearly normal. You wouldn't have to make a histogram. So how do we do this? Well, we would enter our summary data, which up here was a mean difference of 2.2 and 4.1 is the standard deviation. So if you remember when we did that, if I went to stat tests, this is a confidence interval this time. So we are doing number 8, I believe it was. Let's go down and check. It's just a single t interval. And instead of doing data, you go to stats. And this is where you would put in your mean and your standard deviation. So this was 2.2. And this was 4.4. Your sample size was 170. The confidence level was 95. And here we go. So this would tell you that of those couples that you sampled, the mean difference in age between husband and wife was 1.5 and 2.8 years. So again, this wasn't a hypothesis test. You weren't like finding a p-value or anything. You were just trying to figure out what's the typical difference. What gives me a range of possible answers here? So 0 is not in this interval. That would indicate to me that there is a difference in the ages of husbands and wives, and it tends to be with 95% confidence. We can assume the true answer is between 1.5 and 2.8 years, which again, if you follow this work here, they come to that same conclusion. So basically a little summary here. How do you know if it's paired or independent data? Again, think about the before and after effect. Think about if it's a husband and wife or some type of relative. In those cases, you would subtract and account for that as a single set of data and do a paired, like one sample t test or t interval. And if they are independent, then you would stick with the two sample t interval or t test that we did before spring break. Now, for the homework today, just a little brief intro to that to help you. You don't have to use the calculator. This literally is just the following. It says, think about what we're doing, read these situations. Does it sound like you'd use a two sample or paired t method? So you're kind of getting some practice determining if they are dependent or independent, or neither. And again, neither is just thrown in there. If it's a proportion type of question, you wouldn't use either of these. You'd use a z-test. So you're just telling me what you would use. And then when it says here, would you use a hypothesis test or a confidence interval? I purposely chose an example in the notes that was hypothesis test, that was the skaters, and then a confidence interval, that was the married couples. Because essentially, people, if you were left to your own devices, how would you know which one to pick? Basically, confidence intervals are used when you're trying to guess a mean value. Like, you just wanted to know the mean difference in ages between husbands and wives. You weren't trying to determine if there was like some effect that you were trying to measure and then use a p-value and find statistical significance. If you were trying to measure the effectiveness of something, like I gave a treatment to someone and now I'm trying to see if it had an effect, or a pre-test and then a post-test, you might be measuring the effectiveness of your teaching for that unit. That would be a hypothesis test. So these questions here, you're simply trying to determine what type of test you would use, and then if it would be a test or a confidence interval. All right? And you get to skip number 5 because it's weird. So it's really only these 4 questions. So good luck trying those out. Again, we can check answers to that. I'll provide an answer key to that either later today or tomorrow. And again, our goal Friday is to talk about what's going on with the AP test this year and how you're feeling and answer some questions on Friday with a little Google Chat or Zoom, okay? All right, good job, everyone. I'll be in touch with you guys soon.